In my video today, I'll be talking about 20th century physics. First, the photoelectric effect. And this is the fact that raising the intensity of light or increasing the amplitude of the wave could cause the electrons not to be emitted at a frequency if it is too low. This view on light became known as the quantum theory. In this graph right here, you can see that at f of 0, this is going to be your threshold frequency, and this is going to be the minimum frequency required to emit electrons. The slope of this graph is also known as Planck's constant, and you can see the slope and how to find it right here. It is Ke max over F final over F initial. In this diagram is used to show the measure of the energy of the emitted electrons. And the voltage that performs this feat is called the stopping voltage or stopping potential. And Planck's constant, also known as H, is equal to 6.63 times 10 to the negative 34 joules per hertz, or 6.63 times 10 to the negative 34 joules per second. Next, we have the Compton effect and photomomentum. The Compton effect states that colliding photons and electrons obey the law of conservation of momentum. The law of conservation of momentum is displayed here when an X-ray photon collides with an electron and the two forces then deflect and shoot away from each other. And the momentum formula is equal to P equals H over lambda. Next, matter waves. When a photon comes an incident with a crystal of salt, it emerges as a scattered particle, while when electrons have an incident with a crystal of salt, they act as a typical wave in their diffraction pattern. The electron beam, when shot in at a slit, is shown here, and you can see that it acts like a normal molecule would, and it diffracts. The Broglie wavelength is given by lambda equals h over mv, and the Heisenberg uncertainty principle was established because on the atomic scale, or the scale of how small of particles these are going to be, it is impossible to determine precisely both the simultaneous position and momentum of the particle, and you have to use this equation to find where a particle of such small size is going to be located at. Next, we have spectral light. And when a hot source that emits white light is said to be incandescent, its light, when analyzed with a prism, it is broken up into a continuous spectrum of light. This diagram shows that when a hydrogen atom is sent into a slit and then through a prism, you can see that it'll start at violet and then it'll end in red. And all in between there's going to be continuous different spectrums of light. And this is known as the Balmer series. Next, we have special relativity. And all this pretty much says is that no matter what medium light is in, it is always going to travel at 3 times 10 to the 8th. And this speed is also the speed limit of the entire universe, and no other particle is going to be able to travel faster than that. And all of these functions can be used when dealing with special relativity. Next, we have mass-energy equivalence. And mass and energy can be changed into each other and are represented in the function E equals mc squared, where c is the speed of light. And since c is such a large number, it does not result in large changes in mass in everyday items, as one would expect. And an example of this is a cooling coffee mug does lose mass as it radiates away energy, but the mass that it gives off is such a small one that we as humans will never be able to tell. Next, we have the atomic structure and the Rutherford model. Ernest Rutherford came up with the experiment located right here, and pretty much he took a uranium sample, sent it through a lead box, caused radiation to come out, and put it through a magnum. And as you can see, all the different rays that are emitted, beta being negative, gamma being neutral, and alpha being positive, will go in different directions. Next, we have the Thomson model, and the Thomson model is actually incorrect, and it was proved by Rutherford's experiment with this. And this pretty much showed that when a alpha particle moves through, it shows that some particles are going to divert while others are just going to go straight, depending on how close or how far away they are from the positively charged particle. Next, we have the Bohr model, and let's see. Bohr was a Danish physicist, and he gave three main ideas regarding physics. One, electrons do not emit electromagnetic radiation while in a given orbit or energy state. Two, electrons cannot remain in any arbitrary energy state. They can remain only in discrete or quantized energy states. And three, electrons emit electromagnetic energy when they make transitions from higher energy states to lower energy states. The lowest energy state is called the ground state. This diagram shows the different energy levels for a hydrogen atom. And all of these right here are going to be your UV rays. These are going to be your visible light, and these are going to be your IR rays. And as you go farther and farther up each state, your energy is going to become closer to zero. And this equation is what you are going to use to find the energy emitted by a photon. And the needed energy to free an electron from an atom is known as the ionization energy. Next, we have quantum mechanics and the electron cloud model. The Bohr model is limited to hydrogen and hydrogen-like atoms. Erwin Schrödinger developed a new mechanics for atoms and called it wave mechanics, later quantum mechanics. The position of an electron was found by use of the wave function, shown here. The Schrödinger equation, shown here, was created using time-dependent motion in classical physics. And the Pauli exclusion principle, which states that two electrons having the same spin orientations cannot occupy the same quantum state, seem to be a rival theory to the ones that Schrödinger created, but they were actually shown to be equivalent and created the new quantum mechanics laws. Next we have nuclear structure and stability. As you can see here, you can have hydrogen in two different states. Either with just one proton and no neutrons, two protons and two neutrons, and you can see how to write them. 1 hydrogen. This number is going to be your number of neutrons plus protons, and this is your number of just protons. And here, this is your number of protons, and then here's your number of neutrons plus protons. And you can see in lithium 7,3 here that you're going to have 3 protons and then 1, 2, 3, 4 neutrons. And the mass of a proton is 1.673 times 10 to the negative 29 kilograms. Your neutron mass is going to be 1.675 times 10 to the negative 27 kilograms. And your atomic mass unit is going to equal 1.66 times 10 to the negative 27 kilograms. And this is equal to 1/12 the mass of a carbon-12 isotope. Next we have bending energy. And this pretty much states that the experimental weight and the actual weight of an atom are going to differ slightly from each other. And you're going to use this equation to find the difference. And this graph shows the average bending energy per nucleon when it is plotted against the atomic number Z. Finally, we have radioactive decay, fission, and fusion. And radioactive decay can either be classified as alpha or beta decay. Alpha decay is when you're going to take an atom and then split it, and it'll result in one atom, and then one element of hydrogen 2, 4. And you are just going to subtract these numbers from your original element, and you are going to come up with a new element, as here it is thorium. In beta decay, you are going to take your original element and you are going to add one electron to it, and your resultant is going to be your new element. In this case, it is Pa-23491. And fission is when uranium-235-92 absorbs slow-moving neutrons and its nucleus splits into 2 smaller nuclei. And this can be shown here when the uranium is added with one neutron, and then it's then split into 2 separate elements. And fusion is combining 2 hydrogen isotopes to form one helium, and can be shown here when 2 hydrogen atoms are combined to get one helium atom. And this particular reaction powers a hydrogen atomic bomb.